Good afternoon, everybody. We'll be getting started here in just 1 minute. All right, good morning. We're going to get started here. My name is Sean Rogers. I am our wireless product manager here at Zyxel. And so today we're doing our presentation on basically Wi-Fi. It's not really looking at our products or our access points. It's looking more at the technology, the environment, things like that, explaining how Wi-Fi works, some of the government agencies involved, etc. As we go through today, if you have any questions, send them in using the question and answer box. That's the box I can see as we talk here. I cannot see chat easily. So any questions, comments, use questions and answers in the Zoom interface. Oh, you know what? I need to start this over on Facebook. Give me just a second here to start this on Facebook. While we do that, some other housekeeping here. For those that don't know, I am still recovering from COVID. This is my first long webinar since coming down with COVID. So I've got a cough drop in my mouth. I hope that doesn't cause too many issues. And, I still may need to stop periodically to drink or to cough. So I apologize for that in advance. But I'll try to answer questions as we go through today as they come in via Q&A. And then at the end, I'll take a look at chat and give you guys times to send in more questions. Okay, it looks like it should be live on Facebook. Make sure we're recording. We are recording. So we'll go ahead and get started. So just a quick background on who Zyxel is for those of you that aren't familiar with us. Let the little animation play here, but we've been making computer networking equipment for over 30 years. We were founded all the way back in 1989. And I believe even our US office dates back to either 1989 or 1990. We've always been in the Santa Ana Canyon. We've moved to buildings a few times, but always the same general area of Anaheim and Placentia. So that is Anaheim, California is where our US headquarters is located. It is where our warehouse is. It is where our tech support staff are. It's where our marketing team is. So when you call in, you are dealing with a Zyxel employee based here out of Southern California. If you call in really early in the morning, you will get transferred to our German office for support. But again, it is Zyxel employees you are dealing with. We are not using outsourced call centers, overseas call centers, other than, that sort of thing. It's all Zyxel employees. And we've got over 100 million devices deployed out in the field. We've been making Wi-Fi products since 802.11, since before they added the A, B, and G onto the end of it. So we've been making Wi-Fi products for a really long time. We had our own chipset company for a while, which has a number of really cool patents when it comes to dealing with Multipath, which led the way for MIMO type applications. That company was then sold to Theros, who then got purchased by Qualcomm. So even on the engineering side, we've got a lot of experience on making the actual chips themselves. So we'll start off here. Bill, I see there's a hand up, but if you have a question, send it in using questions and answers, and I will try to answer it for you. Who are the Wi-Fi players? These are some of the names you are going to see out there. You see the IEEE. These are the ones that actually create the standards that get turned into these Wi-Fi products. So that's why you will see, Wi-Fi often referred to as 11A, 11AX, 11AC, etc. That is a reference to the IEEE standard that defines how Wi-Fi is supposed to work. So they create the standard. There is no enforcement of the standard or anything. They simply debate it, discuss it, write it out, and publish it. And it's generally going to be 802.3, 802.311, and some letters telling you what the standard is. There is the Wi-Fi Alliance. So the Wi-Fi Alliance is an industry group that's behind selling products. So they're behind branding of Wi-Fi. They're the ones that came up with the term Wi-Fi. They are the ones that certify primarily consumer products as being Wi-Fi compliant. So they'll set up the testing requirements and do their own testing if you want your product to be certified by the Wi-Fi Alliance. And they are also the ones that decided to rebrand Wi-Fi from 802.11, ABC, et cetera, to Wi-Fi 4, Wi-Fi 5, Wi-Fi 6, Wi-Fi 6E, et cetera. So you mainly see them playing around on the consumer side, where you'll actually see people paying for the certification. You don't see it too much on business class products, but it goes a long way to ensuring interoperability. That's been, it was a problem in the early 802.11 BG days. One vendor's product might not necessarily talk to another's vendor's product, even though they were both, in theory, based on the same IEEE standard. Right. There was no one out there forcing interoperability. There was no one out there saying, hey, wait a minute, this wording in the official spec could be interpreted differently depending on how you read it. So someone needs to decide how it needs to be implemented. So Wi-Fi fills that sort of gap. And then there's the FCC, the good old US federal government. So they're the ones that set rules for power output. They decide what frequencies we get to use. So when you create a new Wi-Fi product, it has to be certified that it complies with the FCC rules. The FCC doesn't actually do the testing itself. The FCC has a self-test. So we have to go to an independent accredited lab, submit the products for testing and verify we comply with all the rules before we can import and sell the product in the United States. Now, there have been issues in the past with certain other companies who shall remain unnamed, who submitted one sample with one set of specs for certification and then shipped product that didn't comply with FCC. In the past, they ended up having. And this comes back to the FCC doesn't do a lot of enforcement generally. It required another company here in this industry to sue that player for violating the rules and force them to comply. So it's something to keep in mind. It is something also we have seen with reviews, where review units, if not purchased through Amazon or something, are sent out to companies that are cheesed a bit to make them perform better. But by doing so wouldn't actually comply with FCC testing. So it's good the FCC is there. Unfortunately, they're not as aggressive about enforcement as I personally would like. So we'll talk about radio waves. So 802.11 Wi-Fi, it works using radio waves. These are the same sort of radio waves you use for TV, you use for radio, walkie-talkies, etc. It's all the same basic stuff, just in different parts of the spectrum. So just some general things when it comes to it. As frequency goes up, the more data that can be encoded into it. It's one of the reasons why, AM stations generally don't do a lot of music, because the music doesn't sound too good on AM versus FM. And though as frequency goes up, the range gets less. So again, looking at the radio situations, FM radio signals don't travel anywhere near as far as AM radio stations. Anyone who's made a cross-country trip knows that pain of being out in the middle of nowhere and only being able to get that one AM radio station. And we saw the same thing with cordless phones in the home, right? For those of you that are old and ancient like me, you probably remember the old 900 megahertz phones. Sound quality wasn't too great, but you could walk anywhere holding that phone and maintain a phone call. We used to be able to walk across the street to my friend's house and still be able to be on the phone. So after that came the 2.4 gigahertz phones. And when we went to those, frequency went up, sound quality went up, but range became less. And then the 5 gigahertz phones came out. So with 900, you used to be able to, like I said, to walk across the street. With the 2.4, you got okay coverage out in your yard a little bit, but you couldn't go farther than that. And then when 5 gigahertz came out again, quality went up, but you had less range. So now, you had difficulty. You probably couldn't go outside unless you were really close to where the transmitter was. Maybe even some parts of your house weren't covered. So those are the same frequencies that Wi-Fi traditionally is used. Wi-Fi uses that 2.4 and that 5 gigahertz spectrum. So why do we use that? That's because in general, if you want to broadcast radio signals, you have to have a license from the government. Your product has to be certified, and you yourself to operate it need to be licensed. So what the FCC did is they've opened up these little chunks of spectrum here on the bottom of the screen that are available basically for anybody to use. There are rules as far as power output and behavior and things like that, but you don't need a license. So anybody can buy a product in these areas and use it. So that's where Wi-Fi exists. But of course, there's lots of other non-Wi-Fi products that are also using those exact same chunks of spectrum, because those are the chunks of spectrum that everybody has to share, whether it be an RC car or a cordless camera. I mean, anything that's wireless is using one of these three chunks of spectrum. So when we look at access points and we look at power, generally when you're looking at business class products, you will see power being designated as dBm. This is a logarithmic scale of power, same dBm that you use for measuring, how loud something is. Same thing here. It's telling us how much power is coming out of your access point. So every 3 dB increase is doubling your output power. So 23 dBm is double the power of 20 dBm. Now, consumer products will usually use milliwatts. So why do business products use dBm versus milliwatts? So the one answer is just because it's industry. They expect you know what you're doing. This is the term the scientists and engineers use when they're doing their calculations. And in the old days, when most access points had external antennas, and it was really common for people to remove the stock antennas and add new antennas to them, you can take the dBm output power, add it to the dBi gain of your antennas, and get the total output power with the amplification included. You can also subtract out easily losses due to connectors or cable runs and things like that. So it's really convenient to use dBm and dBi for doing calculations like that. Now, these days, unless you're an outdoor specialist, you're probably not messing with antennas and stuff like that anymore. But it carries over. And again, this is, scientifically and engineering wise, this is how you describe radio waves. Milliwatt, on the other hand, tends to get used on the consumer products because it looks cooler, right? You don't want to say to this person, oh, our competitors are 20 dBm. Our product is 23 dBm, because to somebody who isn't familiar with logarithmic scale here, it doesn't sound like there's that much difference. Whereas if you say to them, our competitors are 100 milliwatt, we are 200 milliwatt, that sounds like a much, much bigger gain, right? And it's much easier to market those numbers. So that's why you generally see that on the consumer type equipment. So a term here that's often used and often overlooked when it comes to Wi-Fi, this is probably the biggest factor when it comes to real world Wi-Fi performance, is this signal to noise ratio. So the signal is that Wi-Fi signal you want to hear that's carrying all your data. And noise is everything else that's also using that same 2.4 or 5 gigahertz spectrum that Wi-Fi uses. So the quality of your connection is primarily going to be dictated by that signal to noise ratio, how strong the signal is compared to everything else that's using that spectrum. So that's why you run into a lot of situations, especially when you get a little bit of ways from your access point or your router, where things don't start performing the way you think they should. Often it's because there's some other source of noise and it's interfering. It also plays a huge factor in the maximum data connection rate you can have. It's one of the reasons why, people will say, hey, wait a minute, I bought this, 1.8 gigabit router. Why is my speed coming in only at, 1 meg per second? It's because there's probably signal to noise ratio is bad. The signal might be good, but there's so much noise that it degrades things so you can't connect at those faster speeds. So attenuation is just, how much this signal is degrading. So basically, as radio waves travel, the degrade, right? That energy that's being carried by those waves gets absorbed. It gets absorbed by the moisture in the air. It gets absorbed into the wood that's building your walls or the drywall or whatever it happens to be. So, as signals travel through open air, they degrade. As they travel through solid objects, they degrade even faster. So we'll take a look here at that formula we've got here. This is the formula if you really want to calculate what your range is going to be. This is kind of how you do it. See, it's not necessarily an easy calculation to do off the top of your head. There's a lot of calculators online you can use to do it. So again, a lot of people used to calculate stuff like this. And if you're an outdoor specialist, you still are probably, because when you're making those outdoor point-to-point links, you need to know this information to figure out how far you can go. But you can see here on the table, we've got some examples here of some common building materials and how much they might be able to affect your signal strength. So you can see here, a simple glass window is going to have, right, your signal strength. It's a 3 dB, up to a 3 dB loss. So it's going to drop the power by half. Tinted windows with that metallic coating on there, they can get all the way up to an 8 dB loss on the signal. And that's, again, just simple glass. And then you start going through walls and stuff like that, you can see it increases. So that's why the range, isn't good, and why when you're trying to cover an area, you want that signal to avoid obstructions as much as possible and to travel through open air as much as possible. So something that people tend to overlook here is that Wi-Fi is a two-way communication. So obviously things here like your signal strength, signal to noise ratio, and stuff like that, the frequencies being used are all going to affect your range. But because Wi-Fi is two-way communication, your range is going to be dictated primarily by the weakest member of that conversation. So we'll take an example here. We'll use me. Me today, my throat's doing pretty good. I can talk quite loud. So I can have a conversation with my wife over on the other side of the house, right down the hallway here, from me, from the master bedroom into the living room. As long as we don't have the TV on, noise, right? Signal to noise ratio. As long as the TV and radio aren't on, I can have a conversation with my wife because I can raise my voice. But let's say my wife is still suffering from COVID. She's got a sore hoarse throat. She can't raise her voice. Well, we can't now have a conversation. She can hear me just fine out there in the kitchen area when I'm in the bedroom, but she can't raise her voice loud enough for me to be able to hear and understand what she's saying. So that becomes the limitation. And it's the same thing here with Wi-Fi. And with Wi-Fi, we see some massive differences in power output between different devices, right? So a typical access point these days, a business class access point, once you factor in antenna gain and stuff, is easily 500 milliwatts, maybe even up to a watt of transmit power. But you're talking to an iPhone, and your iPhone has only got 25 milliwatts of output power, right? A huge difference. Even if we convert these back over to logarithmic dBm, it's a big difference between those two numbers. So it's actually that iPhone that's determining your range, not so much your access point. Now, the access point, having a lot of power, is still good, right? Because we're talking about signal to noise ratio, and most data is coming from the access point to your iPhone. Your iPhone isn't normally sending a lot of data back. So it's got a strong signal to noise ratio, so it can download data really fast because of this mismatch. But because it doesn't need to send a lot of data, as long as that signal can reach the AP, it doesn't matter how fast it is for most applications. So that's something there to keep in mind when it comes to this, is, that's going to be what determines it. And so a common example of this that we run into here in the real world is you've done your site survey, everything looks good, you put out your access point, and you find your mobile users, your tablet users, your phone users are having Wi-Fi issues. And they look at their phone and they go, but I have a perfectly good Wi-Fi connection. I've got 3 out of 5 bars on my Wi-Fi. Why is it performing so poorly? And generally the reason for that is because your phone is showing you how strong the signal strength is that it is hearing from your access point or router. It doesn't know how good the signal is back at the access point coming back from the phone. And since, again, we're talking two-way communication, if your phone isn't acknowledging to the access point, hey, I received that data you sent me, send me the next group of packets, the performance drops off. So that's why you see that. It's because your phone has a good, strong signal, but the signal is having difficulty making it back to your access point. So you think you've got a good Wi-Fi connection, but it's actually an unusable connection. Let's talk a little bit here about RF behavior. So RF behavior, we call them radio waves, and the reason we call them radio waves is the look like waves, right? If you were to draw it out, it looks like, you know, you tell someone to draw an ocean wave and you tell someone to draw a radio wave, they look largely the same. And also they perform very similarly in the real world environment when it comes here to visualizing what's going on, right? Wi-Fi is this invisible thing you can't see, yet we all rely on it so much these days. So it behaves, and it helps to think about it this way, as basically like waves being generated by dropping a rock into a pond. You look at what those waves or ripples do in the top of the water, and it's very similar to a lot of the stuff you would expect to see with Wi-Fi if we could visually see Wi-Fi. So basically the signal goes out. For most access points, it radiates out in a nice concentric circle, just like ripples from that rock we threw into the pond. And then when it interacts with objects, things happen. So one thing that can happen here is the signal can hit a solid object and it can reflect off of it. So the signal starts going this way, hits something, and then bounces back this way. It can actually wrap around objects. The signal can hit something solid like this partially, and then it can actually wrap around it. Now, one thing that radio waves can do that water waves can't is it can actually penetrate solid objects. So it can penetrate through this wall here. It's going to get attenuated, so the signal will be lower, but it also can be fuzzed up as it goes through there, or diffracted. You can also hit an object and scatter and make multiple different little waves going out in different directions. And this is going to be important later. We will come back to what we're just discussing here, but we'll move on and we'll come back to it in a little bit. So another problem we have with Wi-Fi, and this is everything up before Wi-Fi 6, excuse me, is that a trade-off from back in the early days of Wi-Fi. So back in the early days of 802.11, right, network speeds weren't that fast. Wi-Fi itself wasn't designed to be particularly fast, nor was it designed to handle a lot of devices at the same time. And because there was such little bandwidth available and little need for it, the optimization was, well, we're not going to have a lot of wireless devices. So rather than do any form of active management of who gets to broadcast when, we'll use what's being shown right here. This is the thought process that a device goes through before it broadcasts its signal. So the device basically says, hey, do I have some data to send? Yes, I do. So then it listens and it says, can I hear anybody else transmitting currently? If the answer to that is yes, there is someone else, it then uses a random number and pauses for that amount of time and then begins the process again. If it listens and doesn't hear anybody, it says, great, I'm going to go ahead and transmit my data. Now, when it comes to Wi-Fi and radios, in general, basically devices take turns transmitting. Technologies such as MIMO allow us to have multiple devices transmitting concurrently. We'll talk a little bit more about it later, but in general, each device takes its turn transmitting. So the AP sends data, it pauses, and lets someone else transmit data back to it or back to another user, et cetera. So this causes problems though with modern day, because modern day, right? We've got a lot of Wi-Fi devices in our home. I've got over, I think, 50 different devices between, smart plugs and Alexa devices and tablets and families' phones and families' tablets and laptops. So you get a lot of devices on there, which was never planned for. And you're using a lot more bandwidth. And really importantly, a lot of you are streaming. A lot of you are using voice over IP things, right? You're doing video and voice calls over, Snapchat, FaceTime, Line, whatever it happens to be. So you start running into issues. So we'll explain one of the issues here for you. It's something called the hidden node problem. So again, what we've got here is you've got your access point here in the middle of the screen, and you've got two client devices in this scenario. Now, this blue circle is the coverage area for the access point. It can hear any user in this big blue area. Now, again, remember we talked about your client devices are normally much lower powered. So what's going on in this scenario here is this client, it's able to send a signal in this yellow area. And imagine a similar yellow circle over here for this client. So they both can easily communicate and talk to this access point, but they are not within range of each other. So if we go back to this formula, right, what happens? Both of them want to send some data. Both of them can listen, and they will not be able to hear each other. So they may decide, hey, I can start transmitting now. And so you'll have two devices or more deciding that they can transmit at the same time. But for the access point, it can hear both of them. So when they both start transmitting at the same time, that signal merges together and turns into a bunch of garbage noise, and the access point doesn't know how to handle it. So that's an issue we run into a lot in denser environments, which causes performance drop-offs in the home. And even in this situation here, even if everybody's within range of each other, they can all hear each other. As you add more and more clients, you're increasing the odds that you're going to have multiple clients that need to transmit at the same time. And both will be two or more of them will be listening at the same time. They will both see the same gap in talking and say, hey, it's my turn. So then you'll have multiple devices decide to transmit at the same time, even without the hidden node problem. So it's an issue that we run into a lot. So another term here I want to talk about is data rate versus throughput. And this is how I am defining these terms. There are lots of different ways to use these terms, but this is how I see it mostly being used in the industry and out in the real world. So the data rate is the speed that you're going to see quoted on data sheets, on websites, things like that, right? When we say AX 1800, we are talking about a device that can transmit at 1800 megabits per second. So that's what's going to get advertised here. This term is also very commonly referred to as a physical rate or the link rate. And it's all the data that's being sent between two different Wi-Fi devices. So that's the data rate you will see. One of the problems you will run into if you read any review of any wireless product on Amazon is you'll see lots of negative reviews saying, hey, this product says it's an 1800 megabit per second data rate, but I'm not getting anywhere close to that. I'm not even getting half that. So why is that? Now, obviously, it could be things like, the client device is too far away from the access point. There's RF interference issues. It may have something to do with spatial streams, which we'll talk about later in today's presentation. But a big common mismatch between these two is because people are measuring throughput, not the data rate. So what do I mean by that? So like in a typical test that someone will do is they will connect to their Wi-Fi network and they will go to speedtest.net and perform a speed test. So that works by transmitting data right from your web browser to the Ookla server, and then vice versa. The Ookla server sends you data, and you measure how long it takes to send that amount of data. So you will find out, hey, okay, this is how fast it is. And you'll say, wait a minute, that's so much lower than the data rate. Why is that? And the reason for that is because you're measuring the data in that file that's being transmitted between the server and your browser. You're not measuring all of the protocol overhead that goes into making Wi-Fi work, right? So Wi-Fi is using radio waves. It's shared with all these other technologies. There's all these other sources of interference that may be out there. So there's a ton of protocol overhead. Now, if you're used to using Ethernet is a dedicated hard wire. It doesn't have to worry about interference issues and things like that. So because of that, there is very little difference between the data rate and the throughput when you're measuring an Ethernet connection. But with Wi-Fi, you can see as much as a 60% difference between the data rate and the throughput because of how much protocol overhead there may be, retransmissions, things like that, which consume a lot of the available bandwidth. You can see we've got the little pie chart here. The data being sent for that speed test in this example is the red area, and everything else is all the other stuff that's not being measured by that speed test, but is data that's being transmitted between those Wi-Fi devices. Okay, so now we'll talk about how do we increase speed. Now, this isn't something for you to do in your home. I'm taking a look at how do we, as a hardware manufacturer, as a chipset manufacturer, how does the IEEE, when we go from one version of Wi-Fi to another, how are they increasing the speeds? What's being done here to make things go faster? So one of them has to do with encoding. One of the areas where we see increased speeds has to do with how many bit encoding, which is basically, how much data can be crammed onto that little radio wave. So, 11N used 64-bit QAM. 11AC takes us up to 256-bit QAM, right? So a big difference there. And then Wi-Fi 6 gives us 1,000 bits on QAM. So that's one of the ways you do it. Now, one of the trade-offs with encoding is it requires a good, strong signal. So if you've got poor signal to noise ratio, it ends up having to fall back to different versions of QAM until it finds one that's reliable. So even though you're using two Wi-Fi 6 devices talking to each other, they may not be able to achieve this 1024-bit QAM. They may have to drop back to 256 or 64. But when speeds are quoted on data sheets, it's always using the best case scenario in a clean room environment. The other thing is spatial streams. And we'll talk a little bit more about this on a future slide. But one of the ways you increase speeds is increasing the number of spatial streams that are being used. And the other way you increase speed is by increasing how much bandwidth you're using. So 11G, for instance, uses 20 megahertz channels. 11N, part of the reason it was able to essentially double the speed from 54 megabits per second to 108 megabits per second was because they doubled the bandwidth that you were using from 20 to 40. And then 11AC and Wi-Fi 6 have increased that all the way up to 160 megahertz channels. And in some cases, you can even do 320 megahertz channels. So let's talk a little bit about this. We'll start by talking about the channels and bandwidth utilization. So the 2.4 spectrum, when you look at your product, will say, hey, I've got 11 different channels to use. But the trick here is that each of those channels for Wi-Fi is 20 megahertz, but there's only around 60 megahertz total bandwidth that's available in the 2.4 spectrum. So what that means is while you see 11 channels, you've only actually got basically 3 that you can use without overlapping. And anytime you've got overlapping of channels, you've got interference, you've got noise, and it degrades your performance. You've really only got 3 channels to use. But remember, from 11G, we're using these 20 megahertz channels, to 11N, we went up to 40 megahertz channels, which sounds great. It allowed us to double, the speeds claimed on the box. But in the real world, are you going to be able to do much with that, right? Especially if you're a business deployment. Because why? There's 60 megahertz available, and one device wants to use 40. So as soon as you add a second device, you've got a minimum of 20 megahertz of overlap between your two devices that are going to interfere with each other. So if you're in an apartment or condos, you're going to get interference with your neighbors. If you're a business and you've got multiple access points, which is common, you're going to have interference. So what happens is you set your device to 40 megahertz, and it will usually automatically drop back to 20, having your throughput, but avoiding interference or reducing interference. So that was why there was a big push starting with 11N, and it really hit its stride with 11AC of moving to 5 gigahertz. Why is that? Because 5 gigahertz has a lot more radio spectrum available. I forget the exact number here, but I believe it's something like 26 non-overlapping 20 megahertz channels, right? So you're going from 3 that are available in 2.4 to 26 that are available in 5 gigahertz. So that's why people wanted to move to 5 gigahertz. So why didn't we all move to 5 gigahertz? Why aren't we there? Well, part of the challenge is, if you remember earlier in one of those first slides, I mentioned as frequency goes up, range goes down. Signals lose their power or attenuate very much more quickly. So that's one of the challenges of using 5 gigahertz. So it was a trade-off. Do we need all these extra channels, or do we need range? So that's why it was a slow transition from 2.4 to 5, and why even today, a lot of products, especially smart home products, are still only 2.4 only. Now, one thing you'll notice on my little chart here is we've got a big chunk here that's colored orange. It says DFS channel. So let's talk about that a little bit because it's important. So originally 5 gigahertz wasn't available for everybody to use. It was licensed spectrum, just like most other parts of the RF spectrum. And we're going to come back to this with 6 gigahertz. And so what happened is there was already existing devices and users using this 5 gigahertz spectrum, the most common of which is radar. Radar uses 5 gigahertz signals. And that's whether this is weather radar for your local TV station or for the National Weather Service, or whether this is radar being used at your local airport. And you may be surprised how many small airports and stuff are around out there that are using some form of radar. Although the really small ones don't, it's all visual. Anyway, tangent there. So anyway, since there's already these devices there to assuage these existing users, the FCC said, well, okay, We're going to open up this 5 gigahertz spectrum for everybody to use, but we have to make sure that it's not interfering with our existing users. So that's where DFS came from. So DFS is dynamic frequency selection. And basically it says that before you broadcast on these DFS channels, you have to listen for a certain period of time, make sure there are no legacy devices there, then you can start using it. But as you're using it, if you ever determine that there is a legacy user starts using that same channel, you have to stop broadcasting. So because of that, there is often issues with disconnection, right? Your access point isn't perfect at determining if it sees some noise, if that noise is a radar device, some other legacy device, or just some interference coming with it from the, the air conditioning unit up on the roof. So it will stop broadcasting and switch channels. So users will get disconnected and then take a few seconds to reconnect. If when it happens, the AP switches to a different DFS channel, there's an even longer delay, right? Because it's got to listen to that channel first before it starts using it. So that's one reason why people don't like to use these DFS channels. Another reason is it takes an additional 6 months to get your product FCC certified to use DFS channels versus only using the non-DFS channels. So in the mad rush to be the first or one of the first guys to market, a lot of products will ship without support for DFS, especially on the consumer side of things. Now, on the business side of things, we do this sometimes too, but we'll normally release a firmware once it's available that opens up the DFS channels once we've been certified to use them. But a lot of consumer products never get that certification. And this is another area where we run into issues. It generates a lot of calls to our tech support in a business scenario where users are bringing their own device. We'll get this call and they'll say, hey, Bob and Steve, they keep getting kicked off the network, or they don't have coverage when they go into the conference room, but everybody else does. Your product's not compatible. And the answer is, well, yes, we are, but anybody's product wouldn't be compatible because the reason they're having these issues is you're using DFS channels. So when they go into the conference room, which is using DFS, they lose their connection back to the one that's back in the office, the AP that's not using DFS, and they can't connect to this one in the conference room because their device doesn't support DFS. So for both of those reasons, a lot of our partners don't like to use those DFS channels. So if you're not using those DFS channels, you lose a big chunk of the spectrum, right? We just went from, I think, 26 or 22, whatever it is, non-overlapping channels. So now we've got just 9 non-overlapping channels, so a big decrease. But again, we were talking about the way we increase performance is we increase the amount of bandwidth being used. So if we look at 40 megahertz channels, we've now only got 4 non-overlapping, non-DFS channels that can be used. So again, we wanted to increase speed. So the first generation of 11AC or Wi-Fi 5 said, hey, we can use these 80 megahertz channels. Right? We've doubled the speed again, but now you've only got 2 non-overlapping, non-DFS channels that you can use in your business. So as soon as you add a third access point, it's going to be overlapping with one of your other access points and going to be causing some interference issues. And then with 11AC Wave 2 and with Wi-Fi 6, we can use these 160 megahertz channels. And so with these, we have to use DFS. And there's only 2 that are available even using DFS. So again, increasing bandwidth is a big chunk of how they're getting the faster speeds with newer technology, but you may not actually be able to use those larger channels because of interference issues, because of how little bandwidth is available. And this is something that Wi-Fi 6E solves, and we'll talk about it here towards the end. So let's talk now about the other way of increasing speed, which is spatial streams. Now, remember, I was telling you when the radio waves go out, they can hit solid objects and bounce off of them. So that was something that was just the bane of existence back in the 11A, B, and G days. It was like the signals go out in a circle, right? It radiates out in a big wave circle here, and it's going to hit different objects in the environment and bounce off of them. So that was something we called multipath. So think of it like it's basically a radio echo, just like a voice echo, right? You shout in a room and you get echoes because your sound bounces off of different surfaces in the room and comes back to you. And if you get more than one echo, it's because you've got your sound bouncing off of different objects that are different distances from you, right? So it takes time takes more time for your voice to hit the roof and come down versus, or opposite way. It takes more time for your voice to hit the far wall and bounce back to you than it does to hit the roof and bounce down to you. So it's the same thing here. You ended up with, you're trying to receive the signal and you're hearing what are essentially radio echoes, making it hard to understand. Now, eventually some smart people, much smarter than myself, said, hey, wait a minute, we can actually take advantage of this. Our access point can have multiple antennas. Those antennas are physically separated from each other, and we know how far apart they are from each other. Our client device has multiple antennas that are, well, not necessarily as far apart from each other as they are in an access point. They are still separate from each other. And because of that, there is going to be lag between those two, or different distances that the signal has to travel, which are going to induce some forms of echo, and we can take advantage of that. And then on top of all of that, there are objects in the room that the signals are bouncing off of. So we can take advantage of that and basically say, hey, we can transmit different data on each antenna using the same frequency. And because of the smart engineering they were able to do, they were able to basically have the listening device say, hey, these are different echoes. Listen to both echoes and then combine them together. So that's where we get the faster speed. So with 11N, excuse me just a second here. So with 11N, the actual maximum data rate of a 11N signal is 150 megabits per second. Yet probably the most common 11N product out there was an N300 device, right? An 11N product that sent data at 300 megabits. So the reason they were doing that was because they could send two different 150 megabit data streams simultaneously, and then the client combines them together for that 300 megabits total. So when you see a device that was advertising itself as, say, N450, that was telling you that it was using 3 different spatial streams. It had 3 different antennas that could transmit different data at the same time. Now, obviously, for this to work, the client device itself also has to support being able to listen to multiple streams. So if you've got an access point that sends 3 streams, but your laptop can only hear and differentiate 2 streams, you're only going to be maxed out at 300 megabits. You're not going to be able to get the 450 that third stream would give you because your client device doesn't support it. So after this was pretty good. Then someone else came along with 11AC, specifically 11AC Wave 2, and said, hey, wait a minute. Rather than send 2 different data streams to the same user and having them combine them together, how about we send different data streams to different user devices? So this solves one of the issues we run into with Wi-Fi, which is you've got a lot of different devices and they have to each take turns. So by using multi-user MIMO, MU-MIMO, you were able to send different data streams from your access point to multiple clients at the same time. So obviously each client device is only getting 150 megabits or whatever, instead of the combined total. But in a lot of situations, that's all it's needed. They don't need a 300 megabit connection, 150 megabits fast enough. So this way you're able to send that data to 2 users and reduce the amount of airtime that would normally be required by half, right? In the 2-stream scenario, where you could have 3 streams and you could have 2 streams going to 1 user and 1 stream going to another, or you could have all 3 streams going to different users. So this was called MU-MIMO, and it only works with 11AC Wave 2. It only worked from the AP to the client devices. Multiple client devices could not transmit data back. That is something that changed with Wi-Fi 6, or at least with some Wi-Fi 6 devices, and we'll talk more about that later. So when you're looking at a data sheet for a business class product, you will usually see Wi-Fi speed given as how many spatial streams are supported. Yeah, there's kind of an assumption that you know what the maximum single stream data rate is for a particular technology, and you can do the math yourselves. So you'll typically see on access points 2x2, 3x3, 4x4, etc. So that's telling you the first number is how many spatial streams your device can transmit, and the second number is how many spatial streams your device can receive. So again, on access points, it's usually the same per radio. Each radio is generally 2x2, 3x3. When you start looking at client devices, it gets a lot different. So it's a lot easier and a lot less horsepower required to listen to multiple spatial streams than it takes to send multiple spatial streams at the same time. So what you see is on mobile devices, which are battery operated and trained to conserve power as much as possible, they will receive more spatial streams than they themselves can transmit back to the access point. So you may see 1x2 or 1x3 or 2x3. So that's just telling you, hey, these are how many streams I can listen to, and this is how many streams I can send back. And generally this mismatch, between being able to hear data faster than you can send data isn't an issue, again, because in general purpose, more data is coming from the access point and going to the client than going from the client back to the access point. Now, there is a tricky one here, which is primarily these days only done by Cisco and Meraki. And that is they will say, our spatial streams are 4x4:3. So it makes you think, hey, there's 4 spatial streams here on both transmit and receive. But the key number here is the number that comes after that colon. The colon is telling you, this is actually how many spatial streams. I've got 4 antennas, and I can use up to 3 of those antennas to listen or transmit or whatever at a time. So I've got 4, but I can only use 3 actually at once. And this is something they do. Some will tell you it's for marketing. It's more like, for those of you that are familiar with like smart antenna technology, Cisco Meraki doesn't use smart antenna, but this is something like a discount way of trying to get some of that benefit. So I've got 4 antennas, and I will use the 3 best ones for each client device type of thing. So you can, you're not locked into just 3 and you have to use those 3. Well, we've got 4 to choose from. So maybe one of those 4 isn't too good, so we won't use that one. I'm probably confusing you guys more, but it's a poor explanation, but that's what we're talking about there. So basically the data rate you're going to see on your Wi-Fi network is a combination of those 3 things. Everything else being equal. How many spatial streams are supported, what modulation type is currently supported, and then how many megahertz wide channels am I currently using. So we'll just stick here with this one with a single spatial stream, 256 QAM. This is an 11 AC product. So you see here, if you're using a 160 megahertz channel, you can get 866 megabits per second data rate, which is usually rounded up to 900 is what we call it. Right, but again, in order to use this, you have to use DFS. So if you don't want to use DFS, you can't use that 160, you can only use 80. So now your data rate has dropped in half essentially to 433. And then if you can't use 80 because there's too much interference, well, then you drop down to a 40 megahertz channel and only 200 megabits throughput. So again, the only difference between those 3 numbers is how large of a channel can currently be supported. So a common question we get is, how many devices can we get on this access point? And the answer is whatever's on the data sheet is wrong. Doesn't matter whose data sheet it is wrong. And we've run into this recently, certain other competitors that have just put ridiculous amounts of users onto their data sheet. So basically what you're seeing on the data sheet is the theoretical maximum users based on the software running on that access point, how much memory is there. How many wireless associations can our access point keep track of is essentially what you're seeing on the data sheet. And you'll see on the data sheet, 128, 256, 512, maybe even 1,000 on some of the stuff. And what you run into here, though, is you're never going to see that many users on a network without compliance. You're never even going to get close. And it has to do with how Wi-Fi can work. Remember, we were talking about before, right? In general, ignoring MIMO, which complicates things, but just a little bit, each device has to take turns transmitting. And depending on what sort of data and things they are doing, is going to determine how much data they have to send and how frequently they have to transmit data. So you're going to get basically users maxing out the available airtime and turns to transmit data long before you get to that whatever number is on the data sheet for how many users you can get. And it's why we can't give you a clean, simple number. Realistically, it's just going to depend on what type of client devices you're using, how fast they can transmit data based on the RF environment they're in, what sort of application are they using, right? If they're just checking email, they don't need a lot of bandwidth. But if they're, streaming HD video from Netflix, they need a lot more bandwidth available, right, to be able to support those streams. Another problem you run into is voice over Wi-Fi. And it's one of the areas where people just generate, from a business environment, generate a lot of complaints. Now, voice over Wi-Fi uses almost no data, right? It's less than 100 kilobit per second stream usually for a voice over Wi-Fi stream. The challenge you run into again is that voice communication has to be real time or near real time, and we all know that frustration of getting on a conference call, or if you've got VoIP phones in your office and you got multiple people on a call, where there's that annoying delay between when you talk and when the other person hears you, and you end up stepping on each other's toes. And that's because the data is being delayed. It takes time to transmit, and the data is going out over the internet, or in this example, over your Wi-Fi network. And some of those packets get lost. Some of them get damaged. So you need to retransmit them. So the more retransmits you have to do, the longer it takes to send that data, the more difficult the phone conversation can be. And right, you don't want packets being dropped. You don't want retransmits, because it makes it hard to hold a conversation. So even though voice doesn't require a lot of bandwidth, it does require a lot of airtime, right? You've got to be continuously sending those packets. And if someone else is sending a packet, you want to send a packet, you start getting that drop off, right? That really annoying thing on those voice calls or those conference calls where you're only hearing part of what they're saying. And that's because packets are being lost or dropped or can't be sent. So Wi-Fi just compounds that on top of what's going on with over the internet connection, because Wi-Fi is this radio waves that are shared, and there's interference and all these other things which can cause issues. And so it limits how many users you can get on that network using voice at the same time before you start having complaints from your users. So here's an example to try to make this make sense. So in this example here, we've got a scenario where we have users using different types of devices, and they are trying to stream a 3 megabit per second stream. You can imagine this is a SD Netflix stream. We can imagine this is an FTP file being downloaded, whatever it happens to be. It doesn't matter. So we're giving you 3 scenarios here, and the only thing we are changing between these scenarios is how many spatial streams are supported by that client device. So if we have a 3 spatial stream access point, which is really common on the business side of things, and you've got a laptop that supports 3 spatial streams, you can get 34 laptops onto that Wi-Fi connection without issue. You won't have issues until you get 35 users on that access point. And you can see here, airtime utilization is 77%, which is pretty good in the real world. Now we change it. The only thing we're changing here is the spatial stream. Signal strength, power output, everything else is the same. But by just dropping 1 spatial stream, now we can only get 21, right? We've lost 13 devices, have to get removed from your access point to maintain each of them being able to have their own 3 megabit per second. And because they're able to transmit less data at a time, their airtime utilization is almost the same, 75%. So now we take away 1 more spatial stream. It's a cheap tablet or a cheap mobile phone. And now we can only support 10 of those 3 megabit streams on that same access point. And the airtime utilization has jumped back up to 77 because they're using only 1 spatial stream, so the data rate's lower, so it's taking them longer to send the same amount of data than it would otherwise with 3 spatial streams. Even though you've got less than 1/3 of the number of users on that access point sharing that airtime. So that's just looking at spatial streams. That's not taking into account mismatches between 11G clients, 11N clients, 11AC clients. It's not taking into account some of those clients are right next to the access point. Some of those clients are in the next room, things like that. So as you can see, it gets really complicated really quick with trying to figure out how many users you can fit on that access point, or if they're all doing different types of data. In this case, they're all using the same type of data. So just to give you an idea of how difficult it really is to be able to say, oh, don't worry, you can fit X number of users on that AP. So we've been talking a lot about interference, right? When multiple devices are using that same radio frequency at the same time. So that's called co-channel interference. right? So we've got a technology that we use. It's designed to help solve it called Smart Antenna. You'll see it on a number of our products. So I want to take a few slides here, sort of explain what Smart Antenna is, how it works, and show you some real world benefits of using Smart Antenna technology. Any of you guys out there that also sell Ruckus or still sell Ruckus, you're familiar with Smart Antenna. Our implementation is a little bit different than theirs, but same basic ideas. You'll see us making some of the same claims here that they do. So basically, this is an example here. A traditional access point is designed to be mounted on the ceiling, and the signal radiates out in roughly a 360-degree pattern. We call it umbrella coverage. So in this example here, we've got two different access points. And as you can see, their signals overlap a little bit. So any client devices that are in this overlap area are going to have some difficulty versus those that aren't in the overlap area. So traditionally what you would do, right, is you'd spend a bunch of time carefully planning out which channels each access point uses, making sure you don't have any access points too close to each other using the same channel. And the other thing you would do, if that didn't work, is you would turn down the output power, right? So you would reduce the signal strength coming from your access points, because again, your AP is traditionally broadcasting a lot more data is broadcasting much more powerfully than your client devices are. So by reducing the output power, you reduce the overlap area, and you, in theory, don't reduce the range all that much, again, because you're being limited by the client devices, not by the AP. The problem when you do this, though, is that you're also lowering your signal to noise ratio. So your performance is going to be degraded. Just instead of being degraded due to interference issues, it's being degraded due to signal to noise issues caused by the lower output power of your access points. We'll skip that slide. So Smart Antenna is designed to solve this. So with Smart Antenna, instead of having this one umbrella shaped coverage, we've actually got an array of antennas built into the device, and we're able to dynamically switch between those antennas based on the coverage pattern we need to generate. So in what's roughly real time, we're able to go through our different antenna patterns and find the antenna pattern that focuses the signal strength towards the wireless client. And in our algorithm also takes into account sources of interference, whether they be other access points or industrial equipment or what have you, to reduce how much of that signal is being listened to by the access point. And the cool thing with this technology is it requires nothing special on the client devices. And unlike beamforming, it even works with mobile devices. As users roam around, we're able to modify and change that antenna pattern to match. So here's some real world examples of this. It looks like we're running long today. I apologize. We've still got a little ways to go. So this is showing you here, this is a real world test in a hotel. So in this hotel, we've gone with the new way of doing hotel deployments where each room has a low powered wall plate AP using the 5 gigahertz channels here. And as you can see on this floor here, there is no other AP using the 100 megahertz or the channel 100. And then on the other floor, there are 2 APs. They're not right next to each other, but they're in the general vicinity using channel 100. So we took one of our APs and we took a Ubiquiti AP. Both are wall plate APs. And the primary difference between the two of them is ours has Smart Antenna and the Ubiquiti does not. So with one AP turned on, we took some client devices, connected to it, and did some speed tests. And you can see here the aggregated throughput between us and Ubiquiti was roughly the same. They even beat us by a little bit here, 404 megabits per second versus 406. And then airtime utilization was 67% for both of us. So that's, of the available time to transmit, how much time was a device spending time transmitting? 67%. So now we'll turn on a second, one of the second APs on that channel 100. And you see here, the aggregated throughput for our product is 785 megabits per second. So if you take all the users on both APs, that's the aggregated throughput. If you look at the Ubiquiti, it's only 555, right? A pretty significant difference between those two because of that smart antenna technology. So how is that possible? It's because the smart antenna is allowing us basically to talk to devices on different APs using that same channel, but without causing interference to each other because of modifying the antenna pattern. So what you see is on the Ubiquiti, they're using 95% of the available airtime. So if anytime you're listening to that 5 gigahertz channel, 95% of the time, a device is transmitting. You look at us, we're at 131%. We've exceeded the theoretical maximum of 100% because the smart antenna allows devices to transmit simultaneously on the same channel without interfering with each other. You turn on a third access point and you see the same thing. Aggregated throughput goes up. We're now over 300, or excuse me, over 900 megabits aggregated throughput, and the ubiquity stays roughly where it was before, just a little over 500. Another thing to notice here is you look, we've got little boxes highlighting each AP's speed, and you'll notice with the smart antenna, each AP is getting roughly the same amount of bandwidth. Where if you look at ubiquity, it's all over the place. You've got one AP that the aggregated throughput on it was 286 megabits per second, and the other one here is only getting 80 megabits per second aggregated throughput. So why is that? It's because they're in a situation where they are fighting with each other over that airtime and causing interference. And you can see here, we've increased our channel efficiency up to 155% of the maximum because you've got that many users, essentially what should be interfering with each other, but not interfering with each other. So now we'll start talking about some of the deployment ideas here and things like this. Another challenge we run into, right, is, APs are designed to be mounted on the ceiling, but sometimes you can't, right? Sometimes you just got to mount them to a wall because of, the environment that you're deploying your access points in. So in addition to smart antenna, we have a cheaper solution that we call dual optimized antennas. And you'll find these on our 500 and 600 series products. So basically, instead of one ceiling pattern, we've got two patterns in here. One designed for the ceiling, one designed for the wall. And we let you choose on a per AP basis where you've installed that AP to maximize the coverage. Right, so if you're mounting on a wall, you use the antenna that's designed for wall. If you're mounting on the ceiling, you use the antenna that's mounted for ceiling. So it's a cheap, affordable way to solve that solution. So just some general mounting tips. You basically want to mount the AP as high as possible over the area to be covered. Again, assuming non-smart antenna, non-dual optimized, your typical access point. Within reason, right? You don't want it to be a mile up in the sky, but you want it as high as possible because what you're trying to do is you're trying to minimize the number of solid objects that signal has to pass through when it travels between the access point and the client and back. So generally, the higher up you put it, it's a lot more just open air that the signal has to go through. There's a lot less chance of it being blocked or attenuated. So one of the things we run into here is a lot of customers will say, hey, I don't want you to mount that AP on the drop ceiling. I don't want you punching holes in the drop ceiling. I don't want you mounting it there for whatever reason. We hear this a lot. So provided your building codes allow it, I suggest just mounting those APs, just laying them on top of the acoustic tile in that drop ceiling rather than hanging it underneath. Why? Because your typical drop ceiling is some loosely packed acoustic tiles, which are basically just like fiberboard or cardboard that are really thin, and they don't attenuate the signal that much. So that way you have an easy way. You just lay the access point on top of that acoustic tile pointed down, and it has pretty good coverage where you're at. You want to put it towards the middle of that acoustic tile because you don't want the metal T-bars that hold up those acoustic tiles blocking the signal or reflecting it. So that's good. Now, if you are installing it above the drop ceiling or onto a real ceiling, you do need to take into account things like conduit that's up there, air conditioning ducts, anything basically that's metal that is going to reflect or block that signal. You want to try to avoid those. And so we don't sell them, but there are third parties that sell standoffs that basically you screw into the actual ceiling and they drop down a meter or whatever it happens to be. And then you mount the access point onto that. So you're still up high, but you're below all the metal things that may be obstructing your signal. And it comes to hotels, generally the umbrella method is going away, or at least it is on mid-tier and higher hotels. And so when I say umbrella is the traditional way of doing hotel coverage was you walk down the hall and every so many rooms, you stick an access point up, and that access point is designed to cover all of those rooms around it. And it worked okay. It worked okay back in the day. But now you've got a lot more devices in that room that may want on the Wi-Fi, right? Each of your kids has a tablet of their own. You need that to get on there. You've got laptops. So in the old days, you had maybe one device on the Wi-Fi. Now you may have 3 or 4 devices on the Wi-Fi. So per room. So as you add more rooms, you can quickly overwhelm those access points. The other thing has to do, again, with consumers are bringing in their own products. And oftentimes they are cheap, inexpensive stuff they bought at Walmart, which is very underpowered or has very poor antennas in it. And that has a problem getting that signal out into the hallway, especially with a lot of hotel rooms where the bathroom directly borders the hallway. So the signal is having to travel through the room wall. It's having to travel through the tiles that make up the bathroom. It's having to travel through the wiring and the plumbing that's in the wall, and then through another wall out into the hallway, and it just doesn't work too well. So the trend is using lower powered APs and putting one per room or one per every other room. From Zyxel, that would be like our WAC 500H or our 5302D-S. And most of those APs have pass-through ports and all sorts of fun, cool little features designed for hotels. So that's where the trend is going. Although we still run into, franchisees of like Best Western or, something like that, that are just like, no, we still want umbrella. We want to buy as few APs as possible. And then we're going to complain all the time that our guests aren't happy with the Wi-Fi. Look for mounting options that aren't obvious how to unlock them or to remove the device, because people will steal access points if you're putting them in the room where people can find them. Most of our APs, you have to use a pen or a stick or something and slide it behind the device to release the lock so you can get it off. And then have the ability to turn off the LEDs. When you're trying to sleep after a long trip, you don't want a green or orange flashing light above your head shining in your eyes. And some people get paranoid about those lights and think maybe they're being spied on or something. So it's a good idea to have something where you can turn off the LEDs if you're mounting the APs in the room. In the public areas, basically plan each area separately. The lobby planning should be different than the attached bars planning, different than the restaurants planning, different than the conference rooms planning, etc. And basically you need to take into account both the size of the area to be covered, but also user density. How many users are going to be getting onto that network, right? You're going to have a lot more people trying to get on the Wi-Fi in a conference room than you are in the hotel bar, for instance. So design them that way. When you're setting up load balancing and client steering, you want to set groups up based on this. You don't want your system trying to load balance a user between the lobby and a room up on the 5th floor, right? So you don't want the APs saying, hey, wait a minute, I'm kind of full, but hey, up in room 540, there's nobody connected. So I'm going to try to push them over to that. So you're going to set up groups and have those groups based on the physical location for doing your load balancing and client steering. And anywhere where you've got either a lot of access points or you've got a lot of users use smart antenna technology, it makes a world of difference. Schools are very similar. Generally, you're going to have at least one AP per room. Bigger rooms, you may have multiple APs per room. And you have to ask, what sort of classroom is this? And there's still a lot of variety out there between schools and even between types of classes in those schools, right? You may have a thing where, in general, each student is going to have a tablet or Chromebook. But in some classrooms, they may never bring those out, or they may only bring them out during open study sessions and they're just researching Wikipedia and things like that. Where in other classrooms, you may have a teacher that rather than use a projector or smartboard, instead streams video clips directly to each student's client device, right? So, you're going to be using a lot more data in those type of environments than in a room where you're just using the computers to do research periodically or to submit your tests, for example. So that you take that into account. But just in general, students and teachers should be on different networks. They should be VLAN apart and only certain applications allowed between those two as needed, right? You don't want the students hacking your teacher's computer or accessing a file share that they shouldn't be sharing type of thing. But in general, once you get above about 20 students, you want to use 2 APs per room. And anything over 30 students, absolutely use smart antenna. Both Nebula and our controller management have a special classroom-based load balancing mode that's specifically designed for these scenarios where you've got, 30 or 40 students coming into a classroom and all connecting to the Wi-Fi at essentially the same time. So let's talk a little bit about Wi-Fi 6. And whoops, I forgot to carry over my new slides. My apologies. Anyway, we'll continue here. So Wi-Fi 6 is still relatively new, so I wanted to spend some time talking specifically about it. It was designed to solve a lot of the Wi-Fi issues that we've been talking about today. So that was why early days it was marketed as high efficiency wireless before being rebranded as Wi-Fi 6. So Wi-Fi 6, 11AX, high efficiency wireless, they're all the same thing. Now, one of the cool things here with it is Wi-Fi 6 is designed to work with any radio frequency. It works with 2.4, it works with 5, it works with 6, and it works with anything else that's going to get opened up. And this is pretty cool because 11AC only works on the 5 gigahertz radio. If you have an 11AC device, that 2.4 radio is still using 11N. So that's one of the cool things about Wi-Fi 6 is it's the first speed boost since Wi-Fi 4 that's come to 2.4 gigahertz devices. It's designed to handle higher densities, whether that means more users or more access points. It has technologies in there that are designed to solve both of those issues. So similar to what Smart Antenna does, but they're using different technologies to do it. So it's complementary to Smart Antenna. So it gets you some of the same benefits of Smart Antenna, but if you combine Wi-Fi 6 with Smart Antenna, they benefit each other. So some of those technologies here that we've got are that higher QAM I was talking about earlier. We've switched from OFDM to OFDMA, which allows you to divide up the RF spectrum and much more granularly between client devices. Wi-Fi 6 gives you the ability with multi-user MIMO to now do multi-user MIMO from the client back to the access point. So it's not only from the access point to the client anymore. So now you can have multiple devices transmitting back to your access point at the same time, freeing up additional airtime for more users. You have spatial frequency reviews. You have the technology that allows you to tag packets so you know who they're intended for. So your access points and stuff can ignore data being sent from nearby APs that aren't intended for them. So Wi-Fi 6 itself didn't actually get approved until Q1 of last year, but there have been products on the market since late 2019, I think, marketing themselves as Wi-Fi 6. So people got ahead of themselves there. And so because of that, a lot of those earlier products don't support all of the Wi-Fi 6 features. In fact, the Wi-Fi Alliance didn't require certain features such as upstream MIMO, upstream multi-user MIMO, until just this year. So you could have a product that has been tested and certified by the Wi-Fi Alliance as Wi-Fi 6, missing a really important feature here up until this year. And the old products don't have to add it. So anything that was certified before this year gets to continue to be certified. And my mouse is not, there we go. The mouse was kind of stuck there. It wouldn't go where it needed to go. You will also see, this is what we're talking about here. So here's an example. So the first generation Qualcomm Wi-Fi 6 chip is missing those features you see in those columns versus no, and they cannot be added via software. So you can't do upstream OFDMA, you can't do upstream multi-user MIMO, you can't use TWT, you can't use BSS color recorders. There's some smart, features there that are missing on those older products. So later generations support all of those. So when it comes to Zyxel products, everything that's 110 and higher, so our NWA 110, WAC 510s, et cetera, they all use second generation or later chips that support the full Wi-Fi 6 feature set. But when you're out there on the market, a lot of the products out there are still using these older chips. In fact, Netgear launched some products late last year that are still using these Gen 1 chips. So why did they do that? Well, it's cheaper. So on the lower end products, in order to save costs, that's one of the ways you save costs is either by using older chips that are missing features or using newer chips, but that don't really have support for those newer features. So you see that with Netgear, you see that with Ingenious, and you do see it with us with our sort of consumer prosumer APs, the NWA 50, 55, and 90. They are missing some of the Wi-Fi 6 features in order for them to be able to compete with those low-end $89 Netgear and Ubiquity products. Now, Ubiquity went about saving money a different way. Ubiquity only puts Wi-Fi 6 on their lower-end APs on the 5 gigahertz radio. So when you buy their Wi-Fi 6 UAP-AC Pro, for instance, or excuse me, U6 Pro, it's still Wi-Fi 4 on that 2.4 radio. So something to keep in mind. These are some ways here where, Wi-Fi 6 may not necessarily be what you're expecting or maybe missing features you're looking for. So all Zyxel products, including our cheaper ones, that are marketed as Wi-Fi 6 have Wi-Fi 6 on both radios. But again, several of the Ubiquiti SKUs don't, and there may be other vendors that also do not. So let's talk about Wi-Fi 6E. So Wi-Fi 6E is basically something where the FCC decided to open up a huge chunk of this 6 gigahertz spectrum for non-licensed use. So it gives us 2.5 times more capacity than 2.4 and 5 combined, I believe. It gives us a 760 megahertz non-overlapping channels. And there's no interference simply because basically there's nothing else using 6 gigahertz in general in your home that's going to cause interference or in your office. Now we do still have, and so here's an example here of just how many channels 6 gigahertz opens up for us versus 2.4 and 5. So I mean, it's a huge game changer as far as the amount of channels that are available. So Wi-Fi 6E or 6 gigahertz channels are really good for high density environments or environments where distant range is short, but you need a lot of data sent at a time, such as streaming virtual reality. Oops, I'm missing a slide here. I apologize. Oh, I see what I did. I forgot to unhide some stuff. Anyway, it's also really good for backhaul if you're doing mesh. So you can have a dedicated 6 gigahertz channel for your backhaul for your 2.4 and 5 gigahertz users. But there are some concerns with it. So 6 gigahertz was already in use by broadcasters, primarily in utility companies. But those are outdoor uses. So like we have DFS for 5 gigahertz. If you want to do 6 gigahertz outdoors, they have something called automated frequency control. It's designed to be less disruptive than DFS is on 5 gigahertz, so it shouldn't be as big of an issue. And again, it's only required for outdoor use of 6E. The problem we have with it is the FCC hasn't finalized how advanced frequency control is supposed to work. Excuse me, automated frequency control is supposed to work. So we're still waiting on the FCC. That's why we haven't announced any outdoor 6E products yet, because it's in the FCC's hand at the moment. It's very likely that what you will see is you will see products that can support 6 gigahertz or have the hardware to support 6 gigahertz initially launched only supporting 2.4 and 5. And then once the FCC gets everything finalized, a firmware update will be pushed out that enables using the 6 gigahertz radio in those outdoor applications. Again, as frequency goes up, range goes down. So 6 gigahertz range isn't going to be as good as 5 gigahertz, which isn't as good as 2.4. So for those of you with big houses, it may be an issue in your home where you can't get 6 gigahertz throughout your house, or it's slower than you would like it to be because the signal strength isn't good enough. There's some lower maximum power outputs on 6 gigahertz versus like 2.4 or 5. It's not a huge difference though. And then, if you're using 3 different radios, right? A 5 gigahertz Wi-Fi 6 and a 6 gigahertz Wi-Fi 6, that can be a lot of bandwidth that needs to be processed, right? In theory, it could be over 10 gigabits of data that needs to be processed. So it needs some pretty heavy duty CPUs to be able to process that much data. So because of that, you're going to see a lot of business class APs that you can use either 5 or 6 gigahertz, but you can't use them both at the same time. So you'll have one radio that's 2.4 and then one radio that's 5 or 6, depending on what you want to use, as a way to keep costs down. And then of course, here in these early days, it's going to be a while before 6E compatible products are available out on the market, right? So, it's going to be a while before it's really something that you need. But those devices that support all 3 channels simultaneously are probably going to be expensive just because of how much horsepower needs to be supported to handle processing 3 Wi-Fi 6 radios simultaneously. And then also, there's still lawsuits going on against the FCC. There's some from some of the mobile carriers out there suing, trying to get the FCC to actually claw back some of the 6 gigahertz frequency and give it to the cellular providers instead of the Wi-Fi users to use. From what I've been reading, it's unlikely to go anywhere, but it is something that's currently actively being litigated. There may be also some litigation, which is tying up that outdoor use as well. So something to think about. So again, Wi-Fi 6E is for these high density Wi-Fi environments and for backhaul. So that's it with today's slide. I think I screwed up a couple slides in there and got them confused where I was at. But anyway, that's it for today's thing. If you have questions, send them in with the question and answer interface. And this is being recorded. It will be uploaded to our YouTube channel, as are most of our webinars. So just go to YouTube and search for Zyxel America channel. And that's the content that we're putting out here in the United States. There's a lot of different Zyxel channels. If you just search for Zyxel. So Zyxel America channel gets you to the US content. And while I wait for any questions to come in, we do have user forums. Those user forums allow you to talk to your other Zyxel users and professionals, help each other. It's also monitored by our R&D and tech support, and they will oftentimes weigh in to answer questions. But they are, even if they aren't doing that, they are monitoring your feedback and getting ideas for which features to add, which features to prioritize, et cetera. It's also usually the first place that security alerts are put out, the first place where release notes are put out, things like that. So it's a great way to stay on top of what's going on. And then you're always welcome to email me directly. My email is seanr@zyxel.com. Sean is spelled S-H-A-W-N, then the letter R at Zyxel, Z-Y-X-E-L.com. Feel free to email me offline. Feel free to give me suggestions, feedbacks, point out things I got wrong in today's presentation, etc. But I appreciate everyone who's turned out. I'm still not seeing any questions coming in. So I'm going to go ahead and end today's webinar. If you do have something, just either email me directly or reach out to your salesperson. Oh, we do have one question here. So Terry is asking, do the NWA 110 and 210 have smart antenna? No, they do not. To get smart antenna technology on the Wi-Fi 6 APs, you need to go up to the 600 series. So that would be the WAX 630S and the WAX 650S. You can also find smart antenna on some of our Wi-Fi 5 11AC products, such as the WAC 5302D-SV2, which is our wall plate AP with smart antenna. And we're in the process of phasing out most of our Wi-Fi 5 with smart antenna. You may still be able to find some of them. We may still have some in our warehouse, or distributors may still have some. So those would be the WAC 6303D-S, 6503D-S, etc. So basically the key thing there is if there's an S at the end of the model number, it's got smart antenna in it. So that just looking at the data sheet, that's a quick way to find it. Where are Zyxel products available? Coming in from James. So if you are one of our resellers, if you are a reseller looking to buy, you would buy products through Ingram Micro, D&H, Synnex, and you do need a Synnex account. Even though they're merging with Tech Data, they haven't fully merged, so you still need your own Synnex account. Wave Wireless and Target Distributing. In general, just from my own experience, Target and D&H are usually the best ones for having a good variety of our stock on hand. For some of the other vendors out there, you may need to ask them to try to drop ship from our warehouse if you're trying to buy it. Now, if you are an end user looking to buy our equipment, it's out there. We sell on Amazon. If you need help with installations, I highly suggest you take a look at one of our VARs. We do have a VAR directory on our website. So VAR is a value-added reseller. It's where and that includes like system integrators, managed service providers, et cetera. So they can hook you up as well. There are some other e-commerce stores if you just need the hardware itself that you can purchase it at. So yeah, those are your options. Buy it through online, buy it through one of our VAR resellers who can also help with installation, site planning, things like that. Or if you're one of our a reseller, buy through one of our distributors. And if you are a reseller and you're not already part of our partner program, join the partner program. With some very small volumes of Zyxel equipment, you can get some really good discounts automatically applied through distribution. So you can save some money and get some margin there. And that is it for questions. So I'm going to go ahead and end things. If you do have something else, just email me directly. Or if you're one of our resellers, reach out to your salesperson, Jacob, Andy, or David, or even Try. You can send the question to them and they'll loop me in, or they'll loop Marcus, our sales engineer, in as needed. But thanks for turning out, guys. Sorry I went a little bit long today. I appreciate those of you that stuck out. Hopefully this was beneficial for you. And again, feel free to email me any ideas you have for future webinar ideas. Thank you.